This video will begin our discussion of the dot product and its properties. In the beginning assignment for this section, we looked over the dot product and how it relates to an angle. Really what it comes down to is this dot product is a form of multiplication of vectors. We're going to have two different forms. There are multiple forms of multiplication of vectors. We're going to focus on two. What the dot product really does, as you seen in your beginning assignment, was that it really measures how much the vectors are working together. It's a number that measures that. If you didn't catch that, maybe go back and look at the numbers again. How we do a dot product, given a vector u and a vector v, if I want to find the dot product of those two vectors, this is what I do. I multiply u1 and v1. And then I multiply u2 and v2. So you multiply your x's together, you multiply your y's together, and you add them. I want you to notice that this dot product is just a scalar. It's not a vector anymore. It's just a number. You should have caught that from our beginning assignment. The dot product of three dimensions with three vectors, it's the same thing. Multiply your x's, your y's, your z's together, add them together. All right, so that is what a dot product is. This is a very useful product that we're going to be using going forward. It's going to tell us a lot of things. We're literally going to use it to the last chapter. Okay, properties of a dot product. That it is commutative, meaning I can do it in any order. It is also distributive, meaning if we look here, if I do a dot product of a sum, it is just the dot product of the two. We're going to use that here in a moment. And then a scalar through a dot product. Notice that if I have a scalar times a dot product, it either can go with one or the other. It does not distribute like a normal multiplication. Zero vector dotted with any vector is zero. That makes sense. Think about the zero vector is 0, 0. So if I multiply components, they get zero. And then the last one we're going to use quite a bit. I want you to remember, recall that this is equal to the square root of v1 squared plus v2 squared, right? That is my magnitude. Now, if I take my magnitude and I square it, I get v1 squared plus v2 squared. The square root goes away. Well, I could keep working here. This is v1 times v1 plus v2 times v2, and this is actually just v dotted with v. So the square removes the square, and then we can see that we have those products that look like a dot product. So we're going to use that actually on this next example. All right, let's do A here. So A says just to find the dot product, so we're going to use this just as practice. Okay, my arrows are getting worse and worse. U dot V. Okay, I'm going to write in the vectors here. 6, negative 2. Times 5, negative 5 times negative 2. So it's the dot product for that. Sometimes this product is called the scalar product, and the reason is because our answer is a scalar. So we got 6 times negative 5 plus, let's do a minus 2 times negative 2. And that's going to get me, that's a negative 30 plus 4, so a negative 26. Okay, so that is my dot product there. We're not going to give it any meaning, just the operation. Right, we have this next one. So we can dot and then multiply. Let's think about what makes sense here. U dot V is going to be a scalar, and then W is a vector. So this is going to be a scalar times a vector. So I really can't change much. So I'm going to do my U dot V, which we already have. We just did it. So we got negative 26 times W. So notice it didn't make sense to say that we could distribute or anything like that, even though it looks like we should be able to. But what would you do with W and V? Would the dot go? Would it be, what's this multiplication here mean? Well, the multiplication means I should have a scalar. So I do that. And I got 26, and then negative 26 times 7, that's 140 plus 42, that's negative 182. Dotting myself. So 2, 4, yeah, okay, cool. Right, so there is that product. It makes sense that this turns out to be a scalar times a vector. Okay, so this next one, all right, I have U, So I'm going to write down u, not in a highlighter. A u is 6, negative 2, dotted with 2 times v. So we could leave that 2 out, dot, and then multiply, or we could go ahead and multiply. I'm going to go ahead and multiply it through. And then the dot product says I just multiplied the components and add them together. So I got negative 60, negative 60 plus 8. So we got negative 52. Right? The dot products are pretty easy to work with, pretty straightforward. Okay, we're going to start this from, I'm going to zoom in here because I'm going to write kind of small. Okay, so this goes back to the thing that we talked about in the box above, that if I have the magnitude of v squared, that's just the dot product of v with itself. So I'm going to rewrite this as exactly that. W minus u dotted with w minus u plus w plus u times w plus u. All right. This, you can think about this like FOIL. So this is w times w minus, and then I'm going to FOIL this out, u dotted with w minus u dotted with w plus u dotted with u. Then we get the same thing here, except for we're going to have a plus for each one of these. Okay, so we have that. Things cancel out, notice. So we get this cancels with that, this cancels with that, and then I get 2, and then these go back to w squared plus, let's go ahead and factor the 2 out, u squared. That's all we got. All right, we're going to use that here in a moment. That's why we went ahead and multiplied that out for practice. All right, so dot products. It's going to be very useful to use. There's not, the application is very, it's clear, hopefully from the assignment that you guys did, but there aren't a whole lot of applications besides we use the dot product within our applications. I hope that makes sense. Okay.